I'm Heige from Georgia Tech. In this talk, I'll present our work, PnPLoc, UWB-based plug-and-play indoor localization. Indoor localization sees many applications in large indoor spaces. People can use it for navigation, recommendations, tracking assets inside museums, shopping malls, libraries, hospitals. But deploying a localization solution for these spaces is not a trivial task. In this work, we ask the question, can we build an indoor localization solution that any building managers can conveniently deploy the system and any person in the building can gain access to it? First, let's identify what the design properties our system should have. From the building manager's perspective, the infrastructure should be easy to deploy and maintain. That means the infrastructure nodes should be plug and play, and we should be able to add a few nodes without breaking the whole system. Also, the localization system should work no matter the size of the building. From the occupant's perspective, the localization service should be accurate and privacy preserving. Also, it should scale well with a large number of users. So one class of localization systems that satisfy the scalability and privacy preserving requirements is passive TDOA systems, where the client can localize itself without needing to transmit. So there are different types of passive TDOA systems, but in general, each type have at least one or several of these problems listed. So some of them are sensitive to clock drift errors. They might have cost and communication overhead. Some of them might be hard to scale, and some of them will have these special nodes, such as reference anchors, that makes large scale deployment difficult. So therefore, we argue fundamental changes are needed to the underlying ranging protocol to satisfy the requirements we laid out. First, we designed a novel passive client TDOA ranging protocol. More specifically, in our system, the anchor nodes perform two-way ranging among themselves, and the client device can compute its TDOAs to the anchor devices just by overhearing the two-way ranging messages. This is the foundation for the other components of the work and one of the major contributions in this paper. Before jumping into the TDOA protocol, let me give a brief refresher to UWB two-way ranging that's in the IEEE standard. There are two formulas we can use to compute the time of flight, but the latter one is much more preferred. Why? In real devices, clocks are not perfect and the clock frequency drifts. Therefore, the measured time intervals are always slightly different from the actual time intervals. Although the clock drift is very small, it can still cause large error in localization if not accounted for. So the clock drift error for these two formulations can be derived as such. And we can do some dimensional analysis on these quantities. So rho, the time of flight is on the order of nanoseconds multiplied by a small quantity. So this term is negligible. These two terms are negligible. On the other hand, DADBs are dependent on processing time and how fast the radio can switch from RX to TX, and is on the scale of milliseconds. As multiplied by a small number, we still get a quantity on the nanosecond scale. So the first formula would have ranging error of several meters unless we force dA equals to dB, which is difficult to guarantee in different hardwares, and it significantly limits the flexibility of the system. Whereas using the second formula, no matter how we choose the system parameters, the clock drift error is always negligible. Therefore, in ranging, a better ranging protocol should null the clock drift error regardless of the system configuration. This is one of the inspirations for PnPLoc. So in PnPLoc TDOA protocol, we still have two anchors devices performing two-way ranging just like before. Now, the tag device over here's the three messages and measure the time intervals RT1 and RT2. We can then compute the TDOA with any one of the three equations. For the interest of time, I will not show the derivations, but please read our paper if you're interested. So how does it work under clock drift? We can also analyze the clock drift error for equation 1 in a similar way. So the clock drift error is expressed in this final expression. And we have TAB, which is the TDOA, and rho AB, which is the time of flight. And they are on the scale of nanoseconds. Multiplied by a small quantity, this error is negligible and it doesn't depend on any system parameters. We did an actual experiment where we compare the PnPLoc TDOA with another passive tag TDOA method. On the ranging error CDF plots, we can see that PnPLoc TDOA has 90% percentile error around only 12 centimeters, and it outperforms the other system. So that's great. With this novel TDOA protocol, we can do TDOA ranging that's scalable, privacy-preserving, and accurate. However, this is one other problem. So geometrically, one TDOA measurement defines one hyperbola. If we have three TDOAs, the three hyperbolas should intersect, which is the location of the tag. But in reality, all measurements have noise. So instead of three hyperbolas, there may be three sets of hyperbolas, and the solver may give any point in this intersection region. This is known as dilution of precision, or DOP, and it depends on the anchor geometry. So the first natural question is, where should we place the anchors to avoid this problem? So we designed a real-time guiding system that tells the technician or the building manager where to place the anchors. Let's see a simulation first. Suppose these two anchors have been placed, and we need to choose whether to place the third anchor at point A or point B. We used a Monte Carlo simulation for hundreds of test points and plotted this heat map based on the tag localization error. We can clearly see geometry A is much better. In the DOP sense, larger angular spacing of anchors should improve localization precision. So we would want anchors to be in equilateral triangles for lower tag localization error. Using this heuristic, we designed the anchor deployment procedure that tries to form triangles close to equilateral triangles. But because of physical constraint in the real world, it may not be physically feasible to place the anchors in exact equilateral triangles. So instead, we define an acceptable region for placing the next anchor that satisfies certain distance and signal strength criteria. And this procedure can continue till the whole floor is covered. To allow anchors to be dynamically added, we exploit the two-way ranging messages between anchors. So in steady state, the anchors would follow a TDMA schedule. To add new anchors, we reserve several contention slots at the end of the TDMA schedule so that the new anchors can join in these slots. Okay, so we just explained why anchor geometry is important and how we exploit the two-way ranging between anchors for anchor deployment and dynamically adding nodes. There's still one more problem. So when the client is walking, from time to time, the client device will receive messages with poor propagation conditions, causing the TDOA to be wrong. And the TDOAs may be coming from a set of anchors with poor geometry. Therefore, PnPLoc tags tries to select anchor combinations and filter results in real time to improve localization precision. So first, we try to throw out the TDOAs with low RX power. Then, for different combinations of anchors, we choose the best anchor geometry in the DOP sense by computing the GDOP, the geometric DOP metric. If the GDOP metric is acceptable, we check the integrity of the answer and report the localization result. Okay, so with anchor selection and filtering, we should further improve the accuracy. With all this, we evaluate the PnPLoc system on devices based on DW1000 chips. The anchor devices were mounted on tripods and were deployed like this. We deployed the system in 3 different environments. So in the first open atrium environment, it's a slightly smaller environment, and it's similar to what is commonly seen in other work. So we did a comparison study with another UWB-based TDOA system. So this scatter plot shows the PnPLoc results with anchor selection enabled. From this error CDF, we can see anchor selection drastically improves localization precision. We repeated a similar experiment in a much larger library building with 11 anchors and 3 co-located tags. All 3 tags showed similar localization results and update rate, demonstrating that having more devices has no effect on the system performance. The 75th percentile localization error is around 0.7 meters. The experiment is again repeated in an even larger research building with size over 2,200 square meters. Here we again observe how anchor selection and filtering reduces localization error. However, there's a trade-off between update rate versus localization precision. The walking path was over 50 meters, and the 75th percentile localization error is around 1.1 meters. To put all these results to context, we compare with state-of-art UWB TDOA systems. So as you can see here, we evaluate our system in the largest area to the best of our knowledge, and we can achieve similar error performances to the state-of-art. Thank you for listening. Please check out our paper if you're interested in this work.